Thank you very much, Mr. Chairman. Good morning, everybody. I'm going to present a sensor system for vapor trace detection of explosives, not all of them, of course, because we didn't have enough time to develop all different kinds of sensors. It was an interdisciplinary work. Chemists were involved, electrical engineers, physicists, to complete this particular job. So what were the objectives? The objectives, so here is a summary of our presentation. I will explain first some objectives, some principles, MEMS sensors used to do that, how do we do functionalization or modification, very shortly how do we do signal processing, some simulation results, some measurement results, how the vapor generator was accomplished, and I will show at the end some laboratory experiments and some measurement results in the real environment. You will see what the real environment I mean. So what are the objectives and the goals? Actually, we wanted to detect landmines. This was our main goal, and also one of the financing party was Ministry of Defense of Republic of Slovenia. We wanted to detect TNT, TDX, NT, and DNT in the air as a vapor traces. And we wanted to reach sensitivity below 1 ppt, which means 1 molecule of explosive in 10 to the power of 12 molecules of air, gas, or whatever. Of course, we wanted to replace bulky and expensive instruments. We want to miniaturize that. We want to have a very good sensitivity and selectivity at the same time. And of course, as I said, we want that this system is very light and very small. What is the principle of operation? So basically we have a polysilicon capacitor, a pair of polysilicon capacitors covered by silicon dioxide. And one of these capacitors in the pair, or in each pair, we modified by appropriate modification. I will show later on what it is. This was the work of our chemists. Here, this picture shows how the TNT molecules attach to the functionalized part, but not on the other part. So on average, one of the capacitor changes its capacitance. Of course, not for very much, because the size or the dimension of the TNT molecule or RDX molecule is very, very small, less than 0.5 nanometers. So by attaching these TNT molecules to the functionalized surface, we change the capacitor of one capacitor and not the other. And of course, we now have to have an instrument which is able to measure this very, very small capacitor difference. We wanted to achieve a capacitor resolution better than 0.5 attofarad per square root hertz. And this is not very easy to achieve, especially in 1 hertz bandwidth, because we want that the whole system, the whole measurement is done in 1 second. In addition, we want to have different modifications which is supposed to be sensitive to different explosives. So this is our MEMS sensor. Actually, it's not a MEMS device. It's not micro electromechanical system, but we use the MEMS process to produce a comp capacitor. This is approximately, the gap is 1 micrometer wide. Each capacitor is 2 micrometers. And it's approximately 3 micrometers high. So this is SEM image. And as you see, we have on each sensor a pair of sensors, in fact, and we will be modifying one of them and not the other. So in this way, we can obey the principle which I explained before. So here is something which I cannot explain you very much because I'm not a chemist. Our chemists did that. It shows you how the linker molecule is connected on one side to silicon dioxide, and on the other side it has a free head to be compatible with molecule of TNT. Here is the XPS analysis of these surfaces, and here is the measurement which shows how stable it is over the time. So we measured immediately after production, immediately after functionalization, and then after some time, 1 month period and 3 months period, and we still get exactly the same composition. So these are the formulas. I will not go into that. So if anybody has any question, please send me an email and I will relate it to our chemists. Now, of course, we have to measure this small capacitive difference, and of course, we would like to measure differently functionalized sensors at the same time. So here is the principle of operation for two capacitive pairs. So one functionalized and one unfunctionalized. This is one pair, and another pair which has different functionalization. Both are connected to our, let's say, transimpedance amplifier, some bandpass filter, some AD conversions, and some digital signal processing. I will not go into that detail because I think this is, in principle, a kind of a lock-in with different, which can handle different and more than one signal. So one signal with one frequency is coming from this pair, another signal is coming from this pair. This has different frequency. So we can use the same measurement path to process both of them, and only in the digital part we can again distinguish between the two. Again, I will not go into the details of that, but this is the, besides the sensor, this is the most sensitive part and the most important part, which actually determines the sensitivity of the whole system. So it's this transimpedance amplifier where all the noise sources, I would say not all, but most important noise sources in the system are presented. So of course you can see the most dangerous one is this one. And we can of course analyze what is their contributions. The biggest contribution of course is this one. And is even amplified by the ratio of this capacitor over the impedance of the whole sensor. I can say that we were able to reach sensitivity than 0.1 attofarad. The excitation frequencies for each pair are high frequencies in terms of, I don't know, 500 kilohertz or something like that. You will see later on the spectrum how does it look like. The major contributor to the noise is, of course, this amplifier. And this is because we were using CMOS amplifier in order to be able to really miniaturize that and implement it in CMOS technology. And as you know, 1/f noise is a major enemy in this case, especially for low frequencies. So this is the spectrum for two capacitive pairs. One is represented by this spectral line, and another one is represented by this spectral line. This was the simulation, system level simulation results. This was for 1 femtofarad, so this is the spectral line. And this was for 0.1 femtofarad, it's this spectral line. And you could see that the dynamic range for 1 femtofarad is enormous. So we can back calculate what is real sensitivity, and we can find out that this is 3.7 to the power of minus 20 farads per root hertz, which is really, really better than we expected. Of course, this is due to a very careful design of the first stage, so the transimpedance amplifier. The whole system looks like that. So we have a PC for storing and presenting the results. We have a Spartan development board where the complete digital signal processing is implemented, and we have ASIC plus sensor. ASIC is actually this one. It's mainly analog part, so all these transimpedance amplifiers, A to D converters, bandpass filters, and so on. Here is the actually analog chip. So this chip plus 2 pairs of sensor plus some external components. This is connected via USB to the FPGA implemented DSP and to the PC via USB. And of course, this is the whole system, which includes battery, our chip, some pipes, and piezoelectric pumps to be able to do the measurements. So this is a vapor generator. This is very important part because we have to measure quantitatively and qualitatively what are our sensitivities. And so we provided a gas tank with valves which controls the flow, and we have glass cylinders which have a constant temperature maintained at 1 millikelvin. Now, the bottom cylinder contains glass wool, which was deposited by TNT or RDX or NT or DNT and so on for each particular experiment. And here we have valves, and we maintain output flow constant by opening either this and this gate or this and this gate. So we have always the same flow. When we open this and this, we get actually half of the vapor pressure of particular element. If we open that and that, of course, we have only nitrogen in this case. Of course, we need to do a calibration before use, and we did that by immersing this tube into the liquid nitrogen, and then the frozen solids and liquid fraction were analyzed by, I will finish very soon, in NMR. So these are some measurement results, and we can see that this is N2 plus TNT, and we've got this 3 ppt per root hertz sensitivity. Here are measured results for RDX on differently modified sensors. And here is one. Here is just one dirty experiment which we want to do in, let's say, so-called real environment to see what happens if the video is working, but the video is